I'm Norman Wappenger, and today we're going to look at isosceles triangles in universal hyperbolic geometry. So it turns out that there are some pleasant and very useful formulas that are associated to these triangles, and we want to derive these formulas. So first of all, a definition. A triangle A1, A2, A3 is called isosceles precisely when at least two of its quadrances are equal or two of its spreads are equal. So this triangle here, for example, A1, A2, A3, that turns out to be a isosceles triangle because this quadrant is equal to this quadrant. Or, in terms of spreads, the spread here is equal to the spread here. Now the equivalence between these two different aspects is demonstrated by this famous theorem. It's usually called Pons Asinorum. Okay? In Euclidean geometry, the theorem is usually stated in terms of angles and distances, but it can also be stated in terms of quadrances and spreads. Namely, two quadrances are equal precisely when the two opposite spreads are equal. And the same theorem is applying here in the universal hyperbolic setting. So if a triangle A1, A2, A3, say, has quadrances Q1, Q2, Q3, and corresponding spreads S1, S2, S3, then Q1 equals Q2 precisely when S1 equals S2. And this is an immediate consequence of the spread law, one of our four main laws of trigonometry, which says that S1 over Q1 equals S2 over Q2 equals S3 over Q3. So if Q1 and Q2 are equal, for example, then S1 and S2 have to be equal. And conversely, if S1 and S2 are equal, then Q1 and Q2 are equal. The rather unflattering name, Pons Asinorum, it comes from the Latin. It means the bridge of fools, a bridge of asses. It means that it's such a basic result that if you can't cross this bridge, then mathematically you're a bit of an ass. Okay. So I need to make a small comment that sometimes, in sort of degenerate cases, we can have a situation where we have two equal quadrances, but the two spreads are not defined. Or we can have two equal spreads, and the associated quadrances are not defined. So just to give you an example of that kind of thing, have a look at this triangle right here. It's got one of its points on the null circle. So that's a null point. Now, this triangle still has the property that this spread here is equal to this spread here. So it deserves to be called isosceles. But if you calculate this quadrant from here to here, well, that's an undefined quadrant. Because if one of the points is null, then there's a 0 in the denominator for our formula for quadrants. So both these quadrances here are undefined. And I'll leave it to you as an exercise to cook up a triangle where the two spreads are undefined, but the two quadrances opposite are equal. Alright, so this is a basic connection between two equal quadrances and two equal spreads. Okay, so it's nice to introduce some simplified notation for an isosceles triangle because of this duplication of values. So let's agree here that in our standard triangle A1, A2, A3, if it's isosceles, we're going to use the following notation. Q1 and Q2, which we're assuming are equal, we'll call them both Q. And the third quadrant, we'll call that R instead of Q3. The two equal spreads here, which are usually called S1 and S2, we'll call them just simply S. And the other spread opposite to the quadrants little r is capital T. So we have these four quantities. Little q, little r are the quadrances, capital S, capital T are the spreads. Okay, so in this case the spread law tells us that capital S over Q equals capital T over R, which we can of course rewrite as R times S equals Q times T. Okay, so with this notation, here is a main theorem. Very important formulas that are valid in this situation. So it's the isosceles triangle theorem. And it says that with this notation, we can express R and T in terms of S and Q. So R is equal to 4 times Q times 1 minus Q times 1 minus S, all divided by 1 minus S times Q, all squared. And T, the spread up here, has a very analogous expression. In fact, it's kind of symmetrical with this one. It's what you get when you replace the Q and the S. So now it's 4 times S times 1 minus S times 1 minus Q, divided by the same denominator, 1 minus S times Q, all squared. So if we know the two equal quadrances and we know the two equal spreads, then we can write down what the other quadrant is and what the other spread is. Important formulas. The proof is an application of the cross law, our most complicated and most powerful trigonometric law. So here's the cross law. And we have to decide which cross law we're going to use, because there are actually 3 of them, one for every vertex. So the cross law involves all 3 quadrances and 1 spread. So which spread are we going to want to use? Well, let's calculate the first formula. So we'll find R in terms of Q and S. So we want the cross law that involves the spread S. So we'll use it, say, at this vertex here. So the 3 quadrances are Q, Q, and R, and then there's the spread S. So what does the cross law say? It says that this quadrant times the contained spread, Q times R times S, minus the sum of all 3 quadrances, Q minus R minus Q, plus 2, all squared, is 4 times 1 minus Q times 1 minus Q times 1 minus R. So 4 times 1 minus Q squared times 1 minus R. Let's rewrite this a little bit. We'll group the R pieces together. So there's an R times QS there and a minus R there. So R times QS minus 1 altogether. And then the other terms, there's a minus 2Q plus 2. We'll write that as plus 2 times 1 minus Q. All of that is still squared. This is just copied here. Now let's expand both sides. It appears that we're in a little bit of a tight situation because this looks like a quadratic equation for R. We're trying to find R in terms of Q and S. But the R is appearing quadratically here and linearly here. So it looks like a quadratic equation. But some magic comes to our aid. So let's look at the left and right hand side separately. If we square this, we get the square of the first term plus twice the product, so twice the product of these 2 terms will be 4 times R times QS minus 1 times 1 minus Q, plus the square of the second term. So the square of this will be 4 times 1 minus Q all squared. But that same expression is sitting over here on the right hand side. 4 times 1 minus Q all squared times 1 is exactly that thing there, so they will cancel. And what's left on the right hand side is just 4 times 1 minus Q squared times minus R, which we'll write as minus 4R 1 minus Q all squared. Now the equation has a common R in all of the terms. So we can cancel that common R, and then there's only a single R left. And we end up with a linear equation. So we'll get an R times this term here squared. We'll bring the other stuff, which now doesn't involve R, to the other side. So imagine we've divided by R, and then we're going to bring this to the other side. There's a factor of 1 minus Q, which is common. There's a factor of 4, which is common. When we bring this to the other side, it changes from QS minus 1 to 1 minus QS, because it negates. And over here what we have is 4 times 1 minus q, the r has gone, with a minus 1 minus q. So q minus 1. Here there's a bit of simplification because the 1's cancel. There's a factor of q that's common. So we get r equals 4 times q times 1 minus q. And the other factor here is 1 minus s. All of that divided by this thing squared, which we can write as 1 minus sq all squared. That's our formula for r. Now, since we know that t equals little rs over q, remember the formula qt equals rs on the previous page. So once we know r, we can get t by multiplying by s and dividing by q. So if we divide this by q, that q disappears, and then when we multiply by s, an s appears where the q used to be. So to go from here to here, we essentially replace the q with the s. There's the formula for t. Let's now connect these two formulas with some earlier ones that we got for equilateral triangles and right triangles. So in an equilateral triangle, we have 3 equal quadrances. So that third quadrant, which we're calling r, is now equal to the common quadrants q. So all 3 quadrants are now q. Well, that formula for r that we established then will now read q equals 4q, 1 minus q, 1 minus s over 1 minus sq squared. And if we cancel the common q's and then bring this denominator up here, we get 4 times 1 minus q times 1 minus s equals 1 minus sq all squared. And that's the formula, or the relation, between the 3 quadrants q of an equilateral triangle and now the 3 equal spreads s. So second application, suppose that we're looking at a special case where the third spread, what we're calling t, happens to equal 1. That's a situation where we have then a right triangle which is also isosceles. Here's an example of that. So this would be a situation where here, at this vertex here, we have perpendicular lines, so it's a right triangle, t equals 1. 2 equal quadrants is q, 2 equal spreads s. So there's our formula for t. Now t is equal to 1, so we have 1 equals 4 times s times 1 minus s times 1 minus q all over 1 minus sq all squared. So we can bring that to the left-hand side, and we can bring this to the other side. 1 minus sq all squared minus 4 times s times 1 minus s times 1 minus q equals 0. And now it's a pleasant little exercise for you. Practice your algebraic skills to expand this out and to see that what you get is actually a perfect square. It's 1 minus s times 2 minus q all squared equals 0 on the right-hand side. Well, if something squared equals 0, then that something itself has to be 0. And so 1 has to equal s times 2 minus q, so s equals 1 over 2 minus q, which I hope you recognize from the last lecture. So this is a nice and important thing to do, is to check our formulas against previous ones, to look at special cases, to connect and examine the algebra, to try to interconnect our various formulas so we get confidence in them. These are new formulas. They haven't been around for hundreds of years, so we want to connect them with each other as much as possible. The theory of isosceles triangles is intimately connected with the idea of midpoints and midlines. So let's remind you, or define again, what are midpoints. I'll also introduce dual objects called midlines. So if we have a side A1, A2, in other words just 2 points, a set of 2 points, then we say that the point M is a midpoint of that side, precisely when, first of all, M lies on the line A1, A2, and it satisfies, in addition, that the quadrants from A1 to M is equal to the quadrants from M to A2. So it's like a point that's somehow halfway between A1 and A2. Now, the theory of midpoints in projective geometry or in hyperbolic geometry here is quite different from the theory in Euclidean geometry. And it takes some getting used to, but it also provides a very rich sort of new flavor to the subject. The key point is that, first of all, midpoints don't always exist. You can find 2 points, A1, A2, for which there are no points satisfying this condition. For example, if A1 is inside the circle and A2 is outside the circle, then there will be no points, M, that satisfy this midpoint condition. So midpoints do not always exist. That's the first point. The second point is that when they do exist, there are 2 of them. There is not just one midpoint. There are 2 midpoints. So in this situation here, that side A1, A2 has a midpoint, which I've called M1, which is about there, and another midpoint on this side called M2. So if you actually calculate this quadrants, you'll find it's equal to this quadrants, just as this quadrants equals this quadrants. It's an interesting feature. We're going to talk a lot more about midpoints, especially when we talk about triangle geometry. Midpoints are a very rich source of all kinds of fascinating things. Now there's a dual notion which we're going to introduce slightly new terminology for. Well, actually new terminology. We're going to introduce the notion of a midline. Okay, so we'll say that the line M is a midline of the side A1, A2, precisely when, first of all, M passes through a midpoint and is perpendicular to the line A1, A2. So a midline is a line that's perpendicular to A1, A2 and passes through either this midpoint or this midpoint. So just as there are 2 midpoints, there will be 2 midlines. There's one midline, there's another midline. And I remind you once again that being perpendicular to this line amounts to nothing more, nothing less than the fact that it passes through the dual of this line. There's the dual of A1, A2. So both midlines are what you get when you connect the dual with the 2 midpoints. There's one midline, there's another midline. And they're both perpendicular to A1, A2. Now, midlines are usually called perpendicular bisectors in Euclidean geometry. And we've chosen not to use this terminology for various reasons. First of all, this is a bit long-winded. And secondly, the duality between midpoints and midlines is better expressed with this notation. So it turns out that there's another way of defining what a midline is, which turns out to be equivalent. That another way of saying it is that a midline is a line which is simply dual to a midpoint. So it turns out that the dual of this midpoint is this midline, and the dual of this midpoint is this midline, expressed here. So the midpoint midline notation, I think, reflects better the duality, the natural duality between these 2 notions. Okay, so we're going to be talking a lot more about midpoints and midlines, and we'll develop the theory that's kind of underlying here a little bit more systematically later on. But right now we just want to take the definitions and apply them and see what they have to say with regard to isosceles triangles. So the midline theorem now says that if B is a point which lies on a midline M of the side A1, A2, then necessarily the quadrants between A1 and B equals the quadrants between A2 and B. So here's A1, A2. There's a midline capital M, any point on this midline, say B, has the following property, that the quadrants to A1 is equal to the quadrants to A2. Any point B, no matter which one you choose on this mid line. And that's a familiar property that perpendicular bisectors have, of course, in Euclidean geometry. That the perpendicular bisector of a side consists of all those points which are equidistant to the two sides. Or in rational trigonometry, they're characterized by having equal quadrances to the two points. Alright, so the proof, not hard. Suppose that the midline M passes through the midpoint little m. Let's introduce a little bit of terminology for some quadrances. Let's say that H is the quadrants between B and M. And these two quadrances here, the quadrants between A1 and M and A2 and M, which we know they're equal because that's a midpoint, we'll call that equal quadrants R. So this quadrant is R and this quadrant is R as well. Okay, now we just use Pythagoras' theorem because we have two right triangles sitting here. There's one and there's the other. In this right triangle, Q2, which is the quadrants between A1 and B, that's equal to R plus H minus the product of R and H. But that's the same thing that's happening over in this triangle. There's also an R and an H, so Q1 is also equal to R plus H minus RH. So this quantity here is both equal to this quadrant and this quadrant, and so Q1 and Q2 have to be equal. And let's emphasize that this is valid no matter where B is. It can be inside or outside. Doesn't matter where the side A1, A2 is. It can be inside or outside as long as it has a midpoint and therefore a midline. So our last theorem of the day is a kind of converse to the previous result. In the last result we said that if we have a midpoint of a side, then anything on the midline gives us an isosceles triangle. And now we want to show that if we have an isosceles triangle, then we can always find a midpoint to the base. That's what this theorem is telling us. It's the isosceles mid theorem. Okay, so it's a bit long because there's also a few formulas in it. So if an isosceles triangle A1, A2, A3 has quadrants Q1, Q2, and Q3, and Q1 equals Q2 equals Q as before, and Q3 equals R as before, and if it has spreads S1 equals S2 equals S, and the other spread S3 equals T, so if that triangle is non-dual, and that means that the point A3 is not the dual of the line A1, A2. Right, so that A3 dual is not equal to A1, A2. Then, this point here, the meet of A1, A2 with the altitude N3. This point is a midpoint, first of all, of the side. So in other words, what we're saying is that if we have an isosceles triangle, and if this point we're assuming is not the dual of this, okay, then we can drop a perpendicular. We drop an altitude. And where that altitude meets the line, the base of the altitude, that is then a midpoint of A1, A2. This is just our formula for the altitude. It's the line joining A3 and the dual of A1, A2, maybe down there. That's how we find an altitude. And the rest of the theorem gives us formulas for the quadrants H from A3 to B. It's equal to S times Q. And a formula for the two equal quadrants is R1 and R2 down here. They're both equal to Q times 1 minus S divided by 1 minus SQ. Well, I think I'm going to leave this to you more or less as an exercise because it's a pleasant application of Thales and Pythagoras. Well, we'll give you an idea of what's really going on, is that we can always drop the perpendicular. We can call that point B. That side is H, that side is Q. So this R1 can be found by Pythagoras' theorem. Right? If you have two of the three quadrants in this right triangle, then you can calculate that third quadrant. And when you do the same thing over here, you're going to get exactly the same formula, because the H and the Q are the same over here as they were over there. That's going to prove to you that R1 equals R2, that we actually get a midpoint. You can actually check Pythagoras' theorem that this is actually the formula that you get for this common value R1 and R2. So whenever you have an isosceles triangle, you know the base has a midpoint. Well, it'll have two midpoints, but in particular it'll have one special midpoint, the point that you get by dropping a perpendicular from that third vertex. Alright, so it's time for some exercises on isosceles triangles. In our first exercise, we're going to compute everything for something which is obviously isosceles. So we're going to look at triangle A1, A2, A3, where A1 and A2 are both on the x-axis. So A1 is of the form A to 0 to 1, and A2 is the form minus A to 0 to 1. In other words, A1 has some coordinate A, and A2 has some coordinate minus A. And A can be anything it wants to be. And the third point, A3, is somewhere on the y-axis. It's of the form 0 to B to 1. Now there's a kind of a harder version to this and an easier version, so maybe it's better to start with the easier version. The easier versions are to look at this triangle in some special specific cases. Say when A is equal to half and B equals 2. Draw the diagram and then compute the quadrants and the spreads of that triangle, and check the relations of the isosceles triangle theorem and the isosceles mid theorem. Then you can do the same thing for different values of A and B. Say A equals 2 and B equals a half. And then A equals, say, 4/3 and B equals 2/3. And then one step up in algebraic sophistication is to look at the same situation with a general A and a general B, where now the quadrants and spreads are not going to be numbers, but they're going to be algebraic expressions involving the variables A and B. We learn more in some way by doing this, because we see how the various quantities change when we move the parameters of the inputs. And I've given you the answers here so you can see if you can work towards these answers. So Q1 equals Q2 is this expression with a minus sign. It's some rational function of A and B. There's Q3 or R. There's the common spread S, the third spread T. And from these you can then check the relations of the isosceles triangle theorem. So we can check that the isosceles triangle theorem really is true, and check the isosceles mid theorem is true. And some fairly sophisticated algebraic manipulations will have to be done. Great practice to hone your algebraic skills. And also to get an appreciation for the pleasantness of the subject. We're not getting kind of arbitrary gobbledygook here. There's some rhyme and reason to the expressions. There's pleasant factorizations that occur. It's almost like magic sort of around every corner. I hope you think that at least. So staying with our notation, where we have, say, two quadrants as Q, two spreads S, the base quadrant, say, R, and this top spread T, show that if R, and this was our expression from the isosceles triangle theorem, our expression for R in terms of Q and S is that, then 1 minus R, so 1 minus this expression, can be rewritten, somewhat remarkably, as 1 square divided by another square. The square of 1 minus Q times 2 minus S all squared. It's starting to look like a familiar thing here. So This is intimately connected, as we'll see later on when we talk about midpoints. The fact that the side A1, A2 here has a midpoint, which we know it does if there's an isosceles triangle on that base, then that's intimately connected with the fact that this quadrant's R has the property that 1 minus it is a square. Okay, and our third and final exercise is another interesting one where we start now not with Q and S, but start with Q and this sort of mid quadrants. The quadrants from A1 to the midpoint of the side A1, A2. And it's this particular midpoint, the one that you get by dropping the perpendicular. So if that's R1, and before we were calling this R2, but we decided that they were equal, so let's call them both R1. That's R1 quadrants, that's R1 quadrants. So in terms of Q and R1, the problem is to find the other quantities. So in other words, find S, find R, find H, find T. And you might like to do it without looking at my answers. So that's the problem. It's an exercise. Use what you know. Try to figure out what these other various things are. And here are the answers that hopefully you will get. So next time we're going to move ahead now to some more applications of the basic trigonometric laws, mainly the spread law now. We're going to look at classical theorems from Euclidean geometry associated with the names of Menelaus, ancient Greek mathematician, and Ceva, or Seva sometimes pronounced. Okay? So Menelaus' theorem and Seva's theorem are very well-known theorems in Euclidean geometry, and we're going to show that they also have analogs here in the universal hyperbolic setting. And somewhat more generally, we're going to include them in a slightly larger framework of theorems which we call the laws of proportion for a triangle. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.